In the last section, we looked at average speed and instantaneous speed. And we noticed with average speed, as our time intervals got smaller and smaller and smaller, we approached our instantaneous speed. This is the idea behind limits, and we're going to look at limits of functions and limit laws in this section. When we talk about a limit, what we're talking about is what happens to a function as the x value approaches a number. For example, if you look at the graph on the top, the graph of f of x equals x squared minus 1 over x minus 1, you'll notice that this function is not defined at 1. If we plug 1 into the formula, we'll have 0 in the denominator, and our function is undefined. So it's not defined at 1. However, as we get closer and closer and closer to 1, you'll notice that the y values get closer and closer and closer to 2. The graph at the bottom is identical to the graph at the top, except that this graph is defined at 1. This is the graph of y equals x plus 1. Both of these graphs have a limit as x gets closer and closer to 1 of 2. Even though the graph at the top, it is not defined at f of 1, it still has a limit of 2. If we took and looked at points very close to 1, so you can see here they start with 0.9 and 1.1, which are each 1/10 away from 1. And as they get closer and closer and closer to 1, as you go towards the bottom of this table, the f of x values get closer and closer and closer to 2. And this is the idea behind a limit. If you look at these three graphs, they all look very similar. The first graph and the last graph are the graph from the previous slide. But notice the graph in the middle. It is a piecewise defined function. For all values except 1, the graph is defined by x squared minus 1 divided by x minus 1. However, at x equals 1, the graph is defined by 1. For each of these graphs, the limit as x approaches 1 is still 2. As we get closer and closer and closer to 1, our y values get closer and closer and closer to 2. Even though in the graph A, f of 1 is not defined. In the graph B, f of 1 is defined, but it's not 2. As we get closer and closer to 1, on each one of these graphs, our y values will get closer and closer to 2. Here are some examples of limits that do not exist. If you look at what is called the unit step function in graph A, as we get closer and closer to 0 from the left, our y values are getting closer and closer to 0, and they're actually all 0 to the left. From the right, as we get closer and closer to x equals 0, our y values are all 1. Since we are not approaching the same y value from the left and from the right, this limit does not exist. So the limit as x approaches 0 of the function u of x, it does not exist. If you look at graph B in the middle, g of x, as I get closer and closer and closer to 0 from the left, my graph is moving down towards negative infinity. As I get closer and closer to 0 from the right, my graph gets closer and closer to positive infinity. Since the limits from the left and from the right are not the same, we're not approaching the same y value from the left and the right, that limit does not exist. If we look at the graph in picture C, the graph f of x, as we approach this 0 from the left, all of the y values are 0. From the right, the y values are defined by y equals sine of 1 over x. You'll notice that this is an oscillating graph, and it just keeps going back and forth between -1 and 1, because all sine values are between -1 and 1. It does not approach any given value. So this also does not exist. In order for the limit to exist, as we approach the number from the left and from the right, we must approach the same number. Now here are some limit laws that we'll need to use in our next recording. What these limit laws say, the first one, the sum rule, says that the limit of a sum is the sum of the limits. The next rule says that the limit of the difference is the difference of the limits. The next one says the limit of a constant times a function is the constant times the limit of the function. The fourth one says the limit of a product is the product of the limits. The fifth one says the limit of a quotient is the quotient of the limits, provided that the limit of the denominator is not 0. The next one says the limit of a positive integer power, or for number 7, a positive integer root, or a root of a function is the integer power or root of the limit. This helps us to be able to compute limits very easily. Theorem 2 tells us that for the limit of a polynomial, the limit as x approaches c of p of x is just p of c. In other words, we can take c and we can plug it in everywhere that we have an x. The same holds for rational functions. If we have a rational function p of x and q of x are polynomials, and q of c is not 0, then the limit as x approaches c is just what we get when we substitute c in for x. So that would be p of c divided by q of c. Now familiarize yourself with each one of these limit laws, because we will be using those in the next couple of recordings to actually calculate limits.